In this video, I'm going to talk about how to perform eigenvalue analysis by using finite element tools like ETABS software. So I'm going to continue with the same example as in the previous video, and it's about a two-story building, 2D frame with two masses and concrete columns by 35 centimeter by 35 centimeter. The story height is 3 meter and the modular of elasticity is 20 gigapascal. So I just run my ETABS and start with a new model. Here we just need to set the display units to the matrix SI. The other parameters are not important in this example since I'm not going to design this structure, I'm just going to analyze it. So I'm going to use SI system of units, and if I press OK, I will be forwarded here. I only need two stories, each story 3 meter, 3 meter, and grid only. For the grading system, I can go with only two grids, like 0 and 3 meters. And yeah, that's it. I proceed to the grading system. Here we are. You can choose which plane you want to work in. I will go with elevation A because it's more obvious in this window. And here we are. Please note that so far we don't have any elements. So I start to draw my element from here. And this one. So I grab these 2 points, assign them to the restraint, and they are fixed. I close all the possible deformations and press OK. Also, I grab these 4 points and assign them to the restraint. And you should take a look at your coordination system. They should be free for the Y translational and Z translational and X rotational. So they should be closed for translational X and rotations around Y and Z because they are out of plane deformations. I want to see this frame only in plane deformations. So if you're working with a 3D model, you don't need to do this part. As the next step, I go to define material. I just add a copy of the concrete material for myself. I name it my material, for example. You can name it whatever you want. This is 0 because I don't want to add any extra loading or mass to the problem. And this is 20,000 megapascal or 20 gigapascal. And I need to grab this window to the other screen to be able to press OK because it doesn't fit here. So I go for define my sections, and I just try to add a new property. And for this one, I will go with the concrete rectangular section, and I name it my section column, and the material should be my material, and the dimensions are 350 millimeter, 350 millimeter. Okay, I make a copy of it. I name it my section beam. The material is material, and the depth, I just put it something like 1 meter, because I want my beam to be rigid. For that assumption that the stiffness of every individual column is 12 EI over L3 would be more correct. So if I press OK, I need to grab my beams and assign them to my section beam, and I will choose 4 columns. You can see 4 elements are selected here. Assign to the frame section, my section column. Okay. So far I've defined the stiffnesses of different elements like material, section properties, and the geometry and support conditions, degrees of freedoms. These are all contribute to the stiffness matrix somehow. However, I also need to define the mass on the structure. If you remember from the definition of the problem, we have 80 tons in the first story and 50 tons in the second story. That's why I grab these points and assign them to joint additional mass, and I will put 40,000 because I have 2 nodes here. So altogether 80,000 kilogram. And I will grab these points and assign joint additional mass 25,000 kilogram, altogether 50 tons. And here we are. We defined our masses, and just take a look at the load cases in the define menu, and you can see dead, live. You know what are dead load and live load, but there is a modal load. If you click on it and press modify showcase, you will see it's a modal load case. You have eigen or Ritz. We are doing eigenvalue analysis, but there is another form of analysis called Ritz analysis or Ritz vectors. That's somehow very similar to the eigenvalue problem, but in a different perspective. For now, we're focusing on the eigenvalue analysis, and here you define maximum number of modes you want. In this case, you only want 2 modes, the 2 first modes of the structure. And if you press OK, you can run your model. You need to save it first. Save it as model number 3. And if you wait for a couple of seconds, you will see the results. So the analysis is completed now, and if you press on the show deform shape, you have cases like dead load and live load. We don't have any loads here in this example. However, you can go to the mode and choose mode number 1 or 2. For now, I will go with mode number 1. And if you press OK, you will see this is mode number 1. And the value is 0.5582. I just write it down here in the Excel. You can find this Excel on the Moodle as well. So I just write that number from ETABS here. And the second mode, if you press this one, or again go to the deform shape option and change this to 2, you will get the second mode as well. So the second mode of vibration has the period equal to 0.2252. I just write it down here. You can see these results are coming from ETABS, and for example, these results are coming from the manual analysis, which I described in the previous video. And there is some minor difference between these two. As you see, this is 0.52, this is 0.55. And the reason is because the stiffness matrix in the ETABS is more precise rather than the manual calculated stiffness matrix. In the manual calculation, we assume that the stiffness of every individual column is 12 EI over cubic L. However, in the ETABS, it's assembling the stiffness matrix in a more precise way by accounting for all the elements and the connection between the beams and columns and everything presented in the finite element model. So the more precise you model your structure, the more flexible you will get your structure and the more values for the T1 and T2. It means that always a finite element model gives you more values in terms of natural period of vibration rather than the manual calculation or even the formulas in the Eurocode, which is somehow like manual calculation. If you remember from previous lectures, we had a simple formula in the Eurocode 8 representing the first mode of vibrations of the structure to be used for seismic loading on the structures. And if you use that one in your example as well, you will see that will give you much less values for the T1. It only gives you for the T1, not T2. And whatever you obtain from ETABS is always more than that formula and always more than the manual calculation. So I've put everything here for the comparison as well. You can see in the previous video we talked about manual calculation. Here we are talking about ETABS, and in the next videos we will talk about different other approaches and we'll compare them here in the comparison spreadsheet. And just not to forget, here is some calculations related to the previous video when I was working manually. Instead of using my calculator, I used Excel just to keep up with all the precisions of those numbers because I'm really working with some really big numbers like these. And if you really miss some of the precisions, you might come with some different results as well. So I used Excel as my calculator just to be precise enough. And here is the stiffness matrix, here is the mass matrix, here is the determinant of that matrix that should be 0. And if you take a look here, when we come here and you want to solve this equation, these coefficients are named A, B, and C. And if you do that, these are the coefficients you need to calculate to come up with omega 2. And then you can calculate omega and correspondingly the natural period of vibrations. And this part is for calculating the eigenvectors like phi1 and phi2. If you really put this equal to omega 1, which is already that one, you will come up with the phi1. And if you put this equal to omega 2 like this, everything will be updated and you will get the phi2 in your calculations. The last point, not least, if you have a start animation button here, you press that, you will see there is a kind of dancing in the structure like this. It means that the mode shapes are relative somehow. It means that, for example, as I described in the last video, The first mode of vibration is 1 and 1.48, or it can be -1 and -1.48. So 1 and 1.48 means the deformation is in the right-hand side, and -1 minus 1.48 means the deformation is in the left-hand side. So if we take both cases into account from one to another and come back, it would be like a dancing you see in the ETABS. And in the second mode, it can be 1 minus 1.08, and another one can be -1 and plus 1.08. For example, in the ETABS, this is the second mode of vibration, and you can see is the first mode of vibration between positive and negative values of the first mode. It's vibrating. So again, I emphasize that this is not the deformation of the structure under any certain external forces. It is the mode of vibration. It's some sort of inherent characteristic of the structure depending only on the mass and stiffness matrices. And but it is the main ingredient to produce the final deformation of the structure under any certain dynamic forces. So if you have any forces, those will be represented as some other extra coefficients into the problem, combining with the mode shapes, producing the final deformation of the structures. And we should note that the first mode of vibration is the most important ingredient in that context. So this is for this video, and thank you for watching, and please proceed to the next one to see how we calculate the same things by using Excel.